Good morning, learners. My name is Mr. Paul Chilola, once again, representing Black Slides Online Tuition. We meet again for a physics class. In which we continue looking at a topic called electric current and potential difference. This is topic number 11 of your Form 3 physics. In today's lesson, we are going to look at yet another electric quantity, which is called potential difference. Potential difference. Potential difference. Remember, this topic is about electric current and the potential difference. So a lot of discussion has been made on the electric current in terms of what it is and how it can be measured in a circuit. Today, we continue looking at the topic with respect to potential difference. What is potential difference? Let's define potential difference. In physics, potential difference or electric potential difference between any 2 points in a circuit is the work done in moving a coulomb of charge from one point to another. Remember from our previous lesson of electric current, in lesson number 2 of electric current, we said that current is the rate of flow of charge in a circuit. So for charge to flow in a circuit, there is need for work to be done on such charge. For the charge to flow in a circuit, we need energy. Energy should be there to do work or to move the charges from one point in the circuit to another point in the same circuit. So that work done on the charge to bring about electric current is what we call potential difference. So potential difference, in other words, is energy, all right, like potential energy, stored energy, all right, stored energy, the energy which will cause the charges to move from one point in the circuit to another. So that's called potential difference. Without this work done or energy, charge cannot flow. In other words, there can never be electric current. So we need energy to move the charge or the electrons around the circuit. That energy which moves electric charge in a circuit is called potential difference. Potential difference. Potential difference is also called voltage. I'm sure you have heard about voltage in Form 1. Alright? So we use potential difference and voltage to refer to the same thing, the same electrical quantity. And so it is measured in units called volts using an instrument called voltmeter. So what are we saying? We are saying that potential difference is the work done in moving a charge from one point to another in a circuit. So potential difference is synonymous with voltage. In other words, you can use the two terms voltage and potential difference to refer to this work done on the charge. So we are saying that without voltage there can never be current. Okay? We need voltage in order to bring about electric current. It is the voltage which pushes electrons or charges in a circuit. So you regard voltage as a pushing force, a force that pushes electrons in a circuit. Alright? It's electric potential difference, also called voltage. Another word for voltage is potential difference, and another word for potential difference is voltage. Voltage. You can calculate the potential difference in a circuit or the voltage in a circuit by making use of a formula. Potential difference is equal to work done divided by charge. So if you know the work done, remember that the unit of work done is the Joule from our previous topics. It's a Joule, and the unit of charge is the coulomb. So you are dividing the number of joules by the number of coulombs. The result you get is potential difference, PD. So we are saying PD, or potential difference, equals to work done per unit charge. If you know the energy required to move an amount of charge, you simply divide that energy by the charge that has been moved. So calculating voltage, this is voltage, mind you, it's voltage. Voltage or potential difference is equal to work done per unit charge divided by charge. Remember, Q stands for charge or quantity of charge. or quantity of charge. So voltage equals to work done per unit charge. So you can write this in symbols as V, where V stands for voltage. Remember, potential difference and voltage are one and the same. So V is equal to W over Q, or work done divided by charge. So the SI unit of voltage or potential difference is the volt. Symbol V. Here you see that the symbol for voltage is a V. The symbol for volt, the unit, is also a V. Okay? In which case, 1 volt of potential difference is the same as 1 joule per coulomb. Remember, work done is in joules. Charge is in coulombs. So you are dividing the number of joules by the number of coulombs. It will give you joules per coulomb. So in a calculation, whatever value you find of joule per coulomb, remember to change it immediately. In your final answer, you should have volts. Let's suppose you got 2 joules per coulomb. Then your final answer will be 2 volts. 2 volts. By the way, the unit volt is named after a scientist who lived many years ago, a physicist, whose name was Alessandro Volta. He's the one who made the first ever battery. He's the first person to use the word battery, and to use the word voltage or volt. His name is or was Alessandro Volta. He made the first battery consisting of 500 cells, from which he generated electricity. So we are saying the unit, or what you call volt today, is actually a unit which is named after Alessandro Volta. For example, if your name is say Yolanda, for instance, your name is Yolanda, and you made, or you came up with, a quantity in physics. Okay, you can name that quantity after your name, or part of your name, as yonder, for example. You can say yonder, a quantity called yonder, named after your name, Yolanda. So the quantity will be named after your name. So in this case, what you call voltage today, you know, the word voltage is in common use. It's also a term which is a technical term at ESCOM, voltage, the electricity that we tap from the sockets, high voltage of 240 volts in your house. All right, it's in volts, named after Alessandro Volta. The first person to use the term volt or voltage is him, named after his name. Okay, so we define a volt, the unit, in the following way. 1 volt of potential difference is defined as the potential difference of 1 joule needed to move 1 coulomb of charge from one point to another. So the potential difference between the terminals of a cell indicates the energy given to each coulomb of charge in a circuit. But if you have seen a cell, or what people mistakenly call battery, you see they indicate the number of volts. What that means is that the cell or battery is capable of providing 6 joules of energy, potential energy, to each charge in the circuit. So that's how we define a volt. So a volt is simply the potential difference of 1 joule needed to move 1 coulomb of charge from one point to another. So that is called a volt. So when you buy a cell, for example, for your torch, check, they indicate 1.5 volts. What that means is that it is capable of providing 1.5 joules to every or to each coulomb of charge when connected in a circuit. So we can calculate the energy given to each coulomb in the following manner. Since we know that voltage is work done per charge, so we can calculate work done by simply making work done W the subject of this formula. Just multiply both sides by Q. Want to make it the subject of the formula, so that W, or work done, is equal to voltage multiplied by charge, potential difference multiplied by charge. All right, but from our previous lesson, we saw that charge is equal to current times time. Charge Q is equal to current times time. So where there is charge Q, we simply replace that with current times time, so that work done now is going to look like this. Work done will be voltage times current times time. Take note of this. We shall come back to this one when we are looking at the cost of electricity which we pay to ESCOM. Yeah, we shall need this equation to calculate the work done, or the energy that we call units, electricity units. Okay, token is calculated using this formula. We shall come back to this one later on. Let's look at an example. We are told that a charge of 10 coulomb a charge of 10 coulombs moved from point A to point B with a potential difference of 3 volts. All right, calculate the energy needed to move the charge. So here, look, a charge of 10 coulombs moved from point A to point B with a potential difference of 3 volts. This W is not needed here. I think it was a typo error. So calculate the energy needed to move the charge. So we need to calculate W. So W, work done, or the energy, is equal to charge times voltage. Charge times voltage. Don't forget that. So all we do is to substitute. So we know the number of coulombs is 10, and the voltage or potential difference is 3 volts. So multiply through, it will give us 30 joules. 10 times 3 is 30 joules. Since we are talking about work done, don't forget that work done is in joules. Joules, eh? So take good note of that. We have taken the number of coulombs times the number of volts. Multiply the two, it will give you energy. Okay? How do we measure voltage in a circuit? To measure voltage in a circuit, we need an instrument called voltmeter. Voltmeter. So we are saying the potential difference of voltage between 2 points, this should be between 2 points, is measured using an instrument called voltmeter. Voltmeter. Just like we looked at different types of ammeters, voltmeters are also of 2 types. Namely, we have analog voltmeters and digital voltmeters. Alright, so a voltmeter is an instrument we use to measure voltage or potential difference. Voltmeter is short for voltage meter. So instead of saying voltage meter, you simply say voltmeter. It measures volts or voltage. So voltmeters can be of 2 types: analog as well as digital voltmeters. I'm sure you have seen this before in your lab. This is a voltmeter. Just like an ammeter, it has 2 terminals, negative terminals. One for the smaller scale, the other one for the larger scale. The black one is a negative terminal. So you connect the black terminal to the negative of the cell or battery, while either this one here or this one, you connect to the positive terminal of the cell. You follow the polarities. So this is called analog. It's analog because its output values are continuous over a range, a given range. So the value can be anywhere between 0 and 3 if you are using the lower scale here, or 0 and 15 if you are using the upper scale. But also you can have a digital voltmeter. It's very rare to see this in schools. Of course, some schools do have. I'm sure your own school also has this. But many, if there is a question to do with measuring electrical quantities, shall recommend this type of analog voltmeter, so that you should practice how to use it and how to connect it in a circuit, as we shall see shortly in this lesson. How you connect this, you need to master that. In very rare circumstances shall you be accorded an opportunity to use this type of voltmeter. So this is called analog. This is a digital one. So in the circuits, when you are drawing circuits, a voltmeter is represented by a symbol like this one here. So you have a V, the letter V, inscribed in a circle. The letter V inscribed. And when you are connecting a voltmeter in a circuit, a voltmeter is connected in parallel with a device across which the potential difference is to be measured. So this is different from how an ammeter is connected. Remember that an ammeter is connected in series with the rest of the components, but a voltmeter is connected in parallel. So like this. So an ammeter is in series, while a voltmeter is across this resistor. This is another form of fixed resistor. The symbol. Alright. So what it is doing here is to measure the voltage dropped at this resistor here. How much voltage of the voltage supplied by the cell, how much of it is being used by the resistor, is being dropped. We say voltage dropped. What is the voltage dropped here at this resistor? So you have to connect it across. This is called parallel, not series. If you look at an ammeter is connected along the same path as the rest of the components. So you have this component here, then ammeter, then a cell. Okay, but a voltmeter is connected across. How much voltage is being used up? How much potential difference is there between the 2 points? This point here and this one. How much energy is this one using? In other ways, so that will be recorded by the voltmeter. Why is a voltmeter connected in parallel? In other words, why isn't a voltmeter connected in series? You face that question in an exam. Why? Why do we connect a voltmeter in parallel and not in series? We connect a voltmeter in parallel or across a component because it contains a coil with a very high resistance. Its resistance, it has an infinite, very high resistance, which when you connect, if you connect it in a series, the high resistance would reduce the circuit electric current. As a result, the components in the circuit would not function properly. So this is the reason why a voltmeter is to be connected across a component or in parallel with a component, a load. So the component can be resistor, as we saw previously, or it can be a lamp or bulb. Just think about anything that consumes electricity. So you can connect a voltmeter across that. in order to measure the voltage dropped at that component. So this is an exam question, 2 marks. Explain why. Explain why a voltmeter is connected across or in parallel with the component and not in series because of its high resistance. Remember, resistance is the opposition to flow. When a resistance is connected in series with the component, current is reduced. Alright, so that's why a voltmeter is connected in parallel with a component.
Welcome to CK Physics. In this experiment, we have the objective of how to connect voltmeters in circuits. I have a source of electricity, a dry cell, and a dry cell holder into which I'll place my cell. And I have an appliance, a bulb, and I have a voltmeter here. I'll bring in the ammeter a little later. For now, I would like to make a complete circuit by connecting the positive terminal of the battery to one end of the bulb, and then from that end, the other end, I'll connect it back to the source. Once I do that, my bulb is able to light, showing that the circuit is complete. Now the next task is to ask ourselves, what is the potential drop? What's the potential difference across that bulb? To be able to tell how much potential difference there is, we'll connect the bulb in parallel to the voltmeter. So let me switch off the circuit for just a moment, and to be able to connect my voltmeter in parallel, I'll connect one terminal to one end of my appliance and connect the other terminal to the other end of my appliance. So we say they are connected side by side. When you connect a voltmeter in parallel with an appliance, you've connected it side by side, and when you complete your circuit by having that switched on, then you notice the voltmeter will deflect and will give you the reading, in this case about 1.5 volts, and that tells you the voltage across the bulb there is about 1.5 volts. If you were to be asked what reason do we have for connecting voltmeters in parallel, the reason is because voltmeters have infinite resistance. And therefore, if you made the mistake of connecting them in series with the appliance, then the appliance will not work at all. Let me do something else about connecting an ammeter and a voltmeter in a circuit to be able to measure the voltage across the bulb and the current through the bulb. To be able to do that, I will connect one end of my cell to the ammeter, and the ammeter is connected in series, so I'll have it along the same loop with my lamp, and you'll notice the ammeter is able to give us a reading of how much current there is, in this case just over 0.2 amps, and the voltmeter is also able to give us a reading. The ammeter is connected in series, the voltmeter is connected in parallel. I want to come back to a point I made a little earlier about voltmeters never being connected in series. The reason we don't want to connect them in series is because their large resistance will block the flow of current, and therefore our appliance will not work. So what I will do is bring my voltmeter here, and from the source, my cell, I connect to one terminal. Just check that every time I'm connecting the positive terminal of the cell to the positive terminal of the device. And in this case, my device, the voltmeter, will be connected to the bulb. And if you notice, the voltmeter is deflecting. It's showing us just over 1.5 volts, but notice that our bulb is not working. The reason it's not working is because there is so little current flowing through due to the large resistance of the voltmeter. So you're always advised, voltmeters must always be connected in parallel with appliances, never in series. Otherwise, your circuit will not work and your appliance will not function. Thank you.
All right. So we got it. Don't connect a voltmeter in series or along the same path as the rest of the components. Rather, connect it in parallel. If connected in series, there will be very reduced current, and therefore the components in such a circuit will not function because the voltmeter has a coil inside it. If you dismantle it just to check inside, you find there is a coil there which has a very high resistance, such that connecting it in series will drastically reduce the current flowing through such a circuit. Now, there are some points that I want you to note when you are using a voltmeter or connecting a voltmeter in a circuit to a circuit. Sometimes when you are doing a practical work in which you are measuring voltmeter, you may notice that the voltmeter is the pointer on the voltmeter or an ammeter moves or deflects in an anti-clockwise direction. Anti-clockwise means from left to right, like the way the arms of a clock move. In a direction opposite to the direction of the arms of a clock. Anti-clockwise, meaning to the left. Then all you have to do is to swap the wires on the terminals of the voltmeter or ammeter. Then you should be able to see the pointer moving in a clockwise direction so that you can take a reading. If it moves to the left or anti-clockwise, simply interchange or swap the wires. Okay. The voltmeter scale can be read in the same way as an ammeter, as we saw yesterday or in the previous lesson. Okay, so the way we take a reading from a voltmeter is just the same as how we do it with the ammeter. These are very important and helpful tips when you are using a voltmeter or ammeter. Check if the pointer is deflecting to the left or anti-clockwise. Please simply swap the wires. Swap the wires on the terminals of the voltmeter or ammeter. Let's look at another concept related to voltage or potential difference, which is called electromotive force. Electromotive force. Electromotive. Alright. We define electromotive force as the potential difference of a cell when it is in an open circuit. Remember, imagine you have opened a circuit, maybe the switch you have opened is open, right? And you measure the voltage. You connect a voltmeter across a cell or battery. Then the reading on the voltmeter is called electromotive force, which is the energy available between the terminals of the cell per coulomb for the complete circuit. Alright, so if both cells, such as this one, for example, they indicate, in some cases they indicate 1.5 volts. If you're buying this for your torch or wall clock, they write 1.5 volts. What that means is that that 1.5 is the energy that is available between the terminals, the positive and the negative terminals, all right, to do work on the charge electrons once it is connected in a circuit. So it's called EMF in short. When the circuit is open, take note here, they'll ask you to define voltage, to give a difference between voltage and the EMF. So you shall use the definitions to say the what? To say the difference between the two. Okay, that's great. So when a switch is open here, then the voltage across the terminals of the cell, this is a cell, the reading on the voltmeter here is equal to the EMF, the electromotive force. So it is equal to the energy available between the terminals of the cell per coulomb for a complete circuit. Alright, so when you buy a cell like this, they indicate, maybe the 1.5 is on the other side, but they indicate 1.5 volts. That one is not a voltage when you measure it before connecting it to the circuit. It's rather an EMF, electromotive force. Electro is for electrons, motive is for motion, so it's a force available, the energy available to move a coulomb in a circuit. Suppose we have 4 cells. We have 4 cells. Such that each cell has a voltage, rather an EMF of 1.5 volts. You can find the total EMF when the cells are connected in series together. So if one cell has this 1.5 volts, then 4 cells will have 4 times as much. So total EMF is going to be the sum of the individual dry cells, in this case the individual EMFs. So you have 1.5 plus 1.5 plus 1.5 plus 1.5. So you add them up, you should get 6 volts. That's what happens if you have a device that uses 2 cells, for example, a torch. If you have a torch that is powered by dry cells, if you have 2, it means the EMF is going to be 2 times 1.5 volts, and so on. Alright, so we come to the end of the lesson, and indeed the end of lesson or topic number 11. In topic number 11, we have looked at the key ideas, key concepts such as current and voltage. By now, you have a full understanding of these concepts. So before I go, I leave with you these questions to do immediately after this lesson, and submit your work as we agreed by taking a picture. By taking a picture of your work, send it to me as a picture. But remember also to write them neatly in your book, because when you are back to school, I shall need to mark all the exercises that you have had. So at this point, this is the end of our topic number 11, electric current and potential difference. Tomorrow we start a brand new topic, which is topic number 12. It's also to do with electricity, but now this is called resistance. So we're going to look at resistance. Topic number 12. For now, I want to go. It's a big bye-bye.